Everybody, and in this video we're going to start discussing for our new kind of module or section here the art of graphing equations, and I'm just kind of trying to sound all dramatic about it, but when I say the art of graphing equations, really you gotta think here. When you start off in algebra, of course, you get to memorize all your basic fun graphs. That is, you talk a lot about lines, or how about parabolas, and I know with my kids a lot we talk about cubics and logs and all these fun graphs, and you get into all these graphs, absolute value, and it is just a giant, library of functions that you end up dealing with. But what I'm going to tell you is this. We're going to start graphing things, at least in, say, a pre-calculus or a trigonometry class, in which you're not maybe used to the graph, but the graph behaves very irregularly, and without a graphing calculator, which I know they're very convenient, but without one, you want to be able to sketch a graph. And this graph could be really important in terms of representing the relationship between two variable values. I mentioned distance and time in a lot of my videos, or maybe money and time, which is important to all of us. So we want to be able to sketch these relationships, and in order to do so, we want to be able to kind of have a nice toolkit of skills for this. Starting with the fact that often when we sketch graphs, we talk about solution points. Okay, so I'm going to start with a very basic function, and that's a really big y, so we'll back up here, but we say, how about we examine this. We say 7 minus 3x, or some of you might be saying, this is y equals negative 3x minus or plus 7, and automatically, I want to point a few things out. Being familiar with algebra, these are both, it's the same function or same equation, but it's a linear equation because, we say the degree of this x value is the first degree. That's linear, okay, one-dimensional, if you will. But the slope of this line is negative. We can go ahead and infer that it's going to be going downhill, and that it has a y-intercept of 7. That is, we say slope was this coefficient of x, and y-intercept is 7, but that's neither here nor there. What I wanted to do was use a very trivial example, and in essence, to kind of talk about solution points and how to sketch a graph. So I will start by saying this. When it comes to sketching graphs this year, one very good tact is to start by isolating one of the two variables on one side of the equation. That is, get it by itself. And in this case, you'll see that y is already by itself. So here's what I'm going to write over here. We say graphing, there we go. Graphing 101, basically. But let's start with this. I'm not even going to tell you to. I'm going to write try isolating. I'm going to go ahead and write y. And in parentheses, I'll write or x. But that's kind of rule number one if you're kind of stuck. And the second thing is this, and then I can't tell kids this enough. They get in front of the ACT, they get in front of a big state test, and they don't do the basics very much anymore. And by basics, what I mean is it is very convenient, especially if you've got a y isolated, to make a table of values. So we'll write this here, make a table. Please and thank you. Seriously, it's like writing out multiplication if you're not sure. Okay, make a table of values, or you can even think of this as solutions. Okay, we're going to say solution points. And so let's go ahead and talk about a solution in the first place. So let's go back over here. You notice we have two variables here, and this is nice because what we'll do is go ahead and we're going to go with this idea of making a table of values. And we'll say x and y, and we'll talk about x as being input, okay, or domain values. That's another word we'll use a lot here. And we say output. But a rule essentially is no more than basically a set of instructions on, if I give you an x value, say how you go about finding the y value. So let's go ahead and select an arbitrary set of x values here. We'll go with the most boring set, but this set of x values here, and we'll go ahead and solve for some y values, starting with -2. Now, well, going back to the rule, we say, okay, everywhere I see an x, everywhere, my suggestion is this, take it out. Take it out and put in a set of blank parentheses, okay? What this is going to ensure is that you don't get mixed up with maybe negative signs. But in this instance, we're saying x is -2. So everywhere I see an x, I'll put this value in. We'll go ahead and evaluate. So we say y equals -3 times -2, of course, is +6. 6 plus 7. We say y is 13. Now, this is a conditional statement. We say y is 13 if x is -2. So we say x, that -2 was the cause of it. But we say 13. Now, knowing our algebra and saying that the slope is -3, or this rate of change is -3, we're saying so for every x, every time x changes by 1, our y value is essentially changing by -3. So we can infer that if we took off -3 from this, we say this is 10. If we took off -3 from this, we say, okay, so this would be 7. But I only know this because it's a line. To be very technical about it, we should be plugging in this -1 value and just kind of showing this here. If I plugged in -1, we would have yielded -3 times -1 is 3, 3 plus 7, and there's the 10 that we essentially would have gotten here. So for the sake of time, I'm going to go ahead and fill in the rest of these values. But again, the point here is this. We're going to call all these coordinate pairs. Oops, let's get that negative in there. These coordinate pairs, these are solution points. And we say solution is only a solution if and only if it satisfies this equation. And the best way to check that is to take these points and plug them back in to see if you get a valid statement. That is, if we had our original equation, how about we go y here? We say y was equal to -3 times x plus 7. Let's pick one of these. We say 1, 4. 1 was the x value, of course, we'll put that here, and 4 the y value, put that here. But we say 4 would be equal to -3 times 1 is -3 plus 7, which essentially checks out. So what we're doing is necessarily looking at a set of solution points, and one good way to find them is to make a table. Okay, so after making those tables, I know number 3 here, and I want us to write it down, is basically plot the points. This is very, very white bread, no crust, okay? Plot the points. So if we plot these points in the xy coordinate plane, kind of thinking about a function as flowing from left to right, we had a few points here, starting with, how about this? We say -2, 13, 2, 3, 4, 5. 2. You notice I put every fifth mark here. It's kind of bigger. We call those benchmarks. And it's a really good habit to have. But we say, okay, so -2, 13. We had -1, 10. Maybe I should switch colors here. -1, 10. We had 0, 0, 7. Doink. And then 1, 4. And 2, 1. So essentially, here's our line right here, and we had a really good idea just by kind of finding some solution points. And you know what, I have to point out, it's going to be a little bit harder to find solution points sometimes, but we got some tricks up our sleeves, okay? But once you got that, number four is just, play a little connect the dots. Connect the dots, okay? Boom. It's awesome. Anyways, this is essentially the outline we're going to be following here, but you know what? You're right if you're thinking that we're going to go back to these algebraic concepts and look at memorizing some essential graphs, such as absolute value, logarithmic graphs, exponential graphs. We're going to be memorizing those, but this is a good toolkit to have before we kind of start doing that.